how to obtain the standard normal distribution moment generating function and also of a normal one. I'm going to prove it firstly of a standard normal, and then by applying the property of linear transformation of moment generating function, I'm going to prove from the for the normal one. Therefore, in this right box, we have the moment generating function of our variable of interest. For here, the one for the normal one, standard normal one, the one for the normal. Let's start with the standard normal. We plug in the definition, and we remember that it is a continuous random variable. Therefore, here we put a exponential tz, and this is the probability density function of a standard normal. Then, at the second stage, we put in the exponent of the exponential our exponential tz, and we apply arithmetic rules, and we get this z square minus 2 times z at the numerator. And here we, by taking a little bit of attention, we can see the square of a difference. Therefore, what we do is that we add and subtract the exponent t square over 2. Therefore, therefore here we have this square of the difference, which is z minus t, and here we have the positive term. Then what do we do? We put outside of the integral the term without the z term, and then we remain with this term, which is exactly the integral between therefore we are taking the integral over all the domain of the standard normal of the normal distribution. Of a normal distribution we mean t, and with standard deviation equal to 1, and therefore by statistics theory we know that this is equal to 1, and at the end we get that what we have what I have drawn in the initial box. Okay, then I'm going to prove this result, applying simply the property of the linear transformation of a moment generating function, which you can see in the video that I put about the general definition of moment generating function and its property. Therefore, x, our standard normal, our normal distribution, it is the linear transformation of z, which is multiplied by the sigma term and shifted by the term mu. We apply the property. Therefore, the moment generating function of x computed at t is simply the product between the exponential power mu t multiplied by the here I made a mistake because it is not computed simply at t, but at sigma t. Otherwise, the result does not hold. Better. Okay, here and then we obtain this result, and then by applying the property of the exponential, we get the same result that I put showed here. And for today is all.